Mr. Willis talking about the membrane. There it is. Beautiful, isn't it? Got a lot of molecules. Let me ask you this. How many molecules thick is the cell membrane?
5.
1,000, 5, 2.
5 to 10.
2 to 6 is 2. It's probably 2. It's 2 molecules.
Andrew and Dylan.
Yeah.
Correctamundo. It's 2 molecules thick. There's a molecule on top. There's a molecule on bottom. You see what I'm saying? 2 molecules separate the outside of your cells from the inside of your cells. That's pretty crazy to think about. So we say that the membrane is semi-permeable. It can let some stuff in, but some stuff can't go through. So what we want to do this section is we want to investigate what stuff can go in and what can't, and how things get in. So the first way of stuff getting in, probably the simplest way, is by diffusion. Diffusion is when substances move from where they are in high concentration to where they are in low concentration. You can see outside of the cell there's a lot of stuff, and inside of the cell there's not much. And so the stuff's going to come from outside to inside. Now obviously whatever these molecules are can go through the membrane. So they must be small enough to fit through. Very small molecules can go through the membrane, but usually the membrane slows them down a bit. Like water is a good example. Water is a small molecule. It can actually go through the membrane, but the membrane slows it down a bit. The molecules will squeeze through very slowly. And so that's kind of what they're showing here. Maybe these are water molecules. And some of them get through. And eventually, you'll even out the concentrations on both sides of the membrane. Now, there are membrane proteins that let water molecules through faster. You know what they're called?
Transport proteins.
What?
Transport proteins?
They have a specific name, though.
Channel.
Yeah, transport.
They're called aquaporins. And they are channel proteins. And they let water in quickly. Other molecules that can go through the membrane easily are uncharged molecules. Water has a bit of a charge to it. So in actuality, as a water molecule tries to go through the membrane, it'll actually, once it gets past these polar heads, it'll be drawn backwards, because the fatty acid tails are nonpolar. And so these are kind of magnetic. So the water molecules, it's actually hard for them to get through. But an uncharged molecule, I'll give you an example of an uncharged molecule. O2, oxygen. That's an uncharged molecule. And electrons are shared equally. There's no polarity to it. And it is not attracted to these polar heads. It'll go right through there. Oxygen will go right through the membrane of the cell. And so oxygen diffuses rather quickly into cells. Why would the molecules, some people think that the molecules, I mean, you have to realize that molecules are always moving. And so imagine these molecules moving around, bumping into one another, and it causes them to, if this molecule bumps into that one, it might get pushed down through it. It causes the molecules to spread out and to fill spaces. The molecules in this room are bouncing around right now. Somebody calculated that one molecule of oxygen has something like 3 billion collisions with other molecules per second. 3 billion collisions per second at normal room temperature. That's a lot of collisions. Are y'all impressed? Molecules move very quickly. Here's molecules coming through a channel protein. We call this not simple diffusion, but facilitated diffusion. Want me to write that word down for you? Oh, here it is. I spell it right here. Facilitated transport or facilitated diffusion. Have you ever heard that word facilitate? If somebody's a facilitator, they make things easier. The protein here is a facilitator. It makes it easier for the molecules to diffuse. These look like they're glucose molecules. They're probably too big to get through the membrane, so they have to go through a channel. The channel's big enough, it's got a hole big enough to let that sugar through. You got me, Chandler? We say that when a molecule goes from where it's in high concentration to where it's in low concentration, that it's moving down its concentration gradient. Let me show it better. This picture's better. Here's where you have a high concentration of stuff. Here's where you have a low concentration of stuff. The concentration gradient goes this way. Often you'll see arrows drawn on something. You want me to draw some arrows? It's fun to draw. How about I use a pen and I draw arrows? Oh, it's a drawing over here. What's going on? This is real weird. I'm freaking out, y'all.
You're in pen.
I wanted a pen, but I wanted to draw it. Oh well, never mind. I was going to draw arrows, but it didn't turn out too well. Sorry. So it moves stuff. The concentration gradient goes from here down, from high concentration to low concentration. That's called concentration gradient. Have y'all heard that term before, concentration gradient?
Yes.
Can you say concentration gradient?
Concentration gradient.
All at the same time?
Concentration gradient.
Not bad. So that's the normal direction of stuff. Now when things are moving down the concentration gradient, they don't require any extra energy. But sometimes some substances will move against their concentration gradient. Oh wait, let's talk about osmosis first. Osmosis is the movement of water across a membrane. Okay? Check this out. Here is a beaker. They have put a membrane in the beaker, a semi-permeable membrane. That means some stuff can get through the membrane and some stuff can't. On this side of the membrane, they have a hypertonic solution. Do y'all remember that word?
Mm-hmm.
It means that there's a lot of sugar or a lot of salt or a lot of dissolved substances. Can you tell there's a lot of dissolved substances over here? On this side, there's less dissolved substances. There's less sugar or there's less salt. What's going to happen here over time is, because there's a membrane in the way, water is going to move from the left side to the right side. Now, just based on what we talked about earlier, are y'all looking at this? You would probably think that these molecules are going to move that way, right? From high concentration to low concentration. Problem is, this membrane will not let those molecules through because they're too big. What the membrane will let through are the water molecules, which are a lot smaller and can get from the left side to the right side here and can go through those spaces, and what you'll see is the water goes through and the side of the beaker fills up with water on the area where there was more salt or more sugar. And so the way I keep this straight in my head is that water always moves to the side with more sugar or more salt or more solute. Water always goes toward the sugar. What would happen if I tried to water a plant with salt water? I pour a lot of salt water on the roots there in the soil. You know what's going to happen to that plant? Water's going to come out of the plant and into the soil. And very quickly the plant will shrivel up. This is what happens. This is why we can't water our crops with salt water. They'll lose water. It doesn't work. Isn't that interesting? Here's what would happen to blood cells if you put them in these different types of solution. If the solution is hypertonic and you put a blood cell in it, hypertonic means a high amount of sugar or salt. Think of the word hyper means you got a lot of sugar in you. If the solution has a lot of sugar in it or salt in it, look what happens to the cells. They lose water and they shrivel up. A lot of kids get these words confused. In this case, the solution is hypertonic. The cell would be called hypotonic. The word hypertonic and hypotonic are words of comparison. So if we have a separation here, a membrane, and on this side we have lots of water, and on this side we have lots of sugar, which side would you say is hypertonic?
Left. The sugar one.
Lottie says left. Is she right? Does anyone vote for the right side? What side's hypertonic? This side's going to be hypertonic. Lottie, you got it right. Good job. The hyper side has more sugar in it. So what would we call this side? Hypotonic. The side with less sugar is hypotonic. These are words of comparison. They're always words of comparison. Hypertonic, hypotonic. What if they're the same on both sides? Do you remember what we call that?
Isotonic.
Then they're both isotonic. If this was pure water, and this was pure water, they're the same on both sides, so we say that they're isotonic to one another. It's impossible to have one side, if we had sugar water on this side and pure water on this side, you wouldn't say that this is isotonic and this is hypertonic. If one side's hypertonic, the other side's going to be hypotonic. So they're words of comparison. That's where kids usually screw this up. Thomas, are you getting any of this? You seem as if you're not. So if you put a blood cell in an isotonic solution, it's just going to remain the same. That's a solution that has the same amount of solute as the cell does. If you put it in a hypotonic solution, then water will rush into the cell. And the cell will swell up and burst. And this picture shows what happens to plant cells in these situations. If the plant cell is in a hypertonic solution, it's going to lose water. That's if you put it in a real salty solution. This is what the plant cells would look like if you watered the plant with salt water. They'd lose water, and the plant cell would shrivel up. The cell wall doesn't move. The cell wall stays in the same place. but the cell membrane shrinks away. We can see this under the microscope. You want to do it? You want to do it
Yeah.
next week?
Yes.
Let's do it. We'll put some plant cells under the microscope. We'll squirt salt water on them, and we'll watch them shrivel. If the plant cell is in an isotonic solution, it just kind of remains the same. And if the plant cell is in a hypotonic solution, water will rush in. The cell will not burst because the cell has a cell wall. Plant cell walls keep their cells from bursting. And so the plant will just stand up really rigid. Is this exciting to you?
Mm-hmm.
You don't seem to care too much. There's a well-watered plant on the right. There's a plant on the left that hasn't had much water. It's kind of shriveled up. You should water your plants when they look like that. Dylan, have you ever watered plants?
I have.
When you water a plant, do you just spray water all over the leaves, or do you spray water at the base of them?
I'll bet the base.
Do you know what the plant wants? It wants water at the base. It pulls water up through its roots, not through its leaves.
I like to give it a little wash though.
Give it a little wash?
Yeah.
Okay. It usually has wax on the leaves that makes the water run off of it anyway. So you're probably not hurting it. Hey, here's a paramecium. Have you ever seen one of these under the microscope?
Yep.
I got some ordered second semester. We'll go look at them. They have special vacuoles called contractile vacuoles. See, Paramecium live in fresh water. So that's a hypotonic solution. Water's always rushing inside their cell. And so what would happen to a Paramecium if water's rushing inside of it? What do you think would happen to it if they didn't do anything?
Burst.
They'd swell up and they'd eventually explode. They have evolved contractile vacuoles. They're vacuoles that fill up with water as the water rushes in, and then they squeeze and they squirt out the water. Would you like to see video footage?
Yes.
Video footage of a contractile vacuole and a Paramecium. Contractile vacuole Paramecium. Here we go. There's no volume. See there, it squeezed. Fills up with water, fills up with water, fills up with water. See, it's got little tubes that lead to it to bring water from all over the cell. See those tubes? And then it squeezes the water out. It's pushing the water out of a little pore in its side that's probably like facing the camera here. So you can't really see the water coming out because the water's clear. Go ahead, squeeze. Up. There's focus. Focus! Okay, here we go. We're going to squeeze. Squeeze the water out. Looks like there's a little hole right there that will go out. Isn't that cool?
Mm-hmm.
So
Squeeze.
they can live in water and
They can live in fresh water. They don't do so well in salt water because they're built for fresh water. But, so they're built to like push as much water out as they can. If you put them in salt water, they'd have to pull water in, and they aren't really built for that. But there are other microbes that are built for salt water. Are you liking this?
Yeah.
That's fun. Very good, isn't it? All right. Now this is called an electrochemical gradient. Are we still in the same section?
I don't think
Did I just leave the section?
I think so.
Are you serial?
Contractile vacuoles are
Alright, hold on. So I got more video footage for you. Contractile vacuole is in this one?
Yeah, it is.
And that's where it ends?
Yes.
Oh. And this section is not as long as I thought. Okay, hold on.
Imagine that you're stranded on a raft in the middle of the ocean. You don't have any emergency food or water, but you also know that humans can only survive about 3 days without fluids. Should you drink seawater or not? Stick with us. We're going to find out and also review hypertonic, hypotonic, and isotonic solutions along the way.
Well, go biology.
Cells have a very finite range of conditions in which they can survive. If it's too hot, too cold, too watery, too salty, too acidic, or too basic, they can't function properly. We're going to explore what happens when you place a cell in a solution that is much more salty, hypertonic, much more watery, hypotonic, or has an equal salt concentration, isotonic. Remember that cell membranes are selectively permeable. They allow certain particles to pass through, but not others. Usually, larger molecules can't fit through the membrane without special channels. The cell membrane is fitted with special protein channels called aquaporins, which allow water molecules to pass through without expending energy. However, the ease with which the water molecules can cross is going to depend on something called the concentration. Concentration is a measure of how much solute there is per volume of solvent. In other words, whether the liquid is more salty or more watery. We'd usually expect that the molecules would follow a process called diffusion. They would flow from areas of higher to lower concentration. Eventually, they will reach equilibrium, where there will be an equal concentration on both sides of the membrane. However, in the case of a liquid like salt water, the salt molecules are much, much too big to fit through the membrane. So the only particle that can move is water. Let's look a little more closely. Water molecules are highly attracted to salt molecules. They cluster around salt and really, really don't want to move. The positive parts of the water molecules stick to the negative parts of the sodium chloride, and vice versa. The interactions between oxygen and sodium and between hydrogen and chlorine are called Ion-Dipole Interactions, which you might remember from chemistry. Water molecules that are not stuck to a molecule of salt are far more likely to relocate. Today we're going to immerse a cell in 3 kinds of liquids: a very solute-rich liquid, a very watery liquid, and a liquid that's in between. Then we'll see what happens to the water molecules. In this first scenario, the liquid surrounding the cell has many molecules of solute in it. This liquid is hypertonic compared to the cell. It has a much higher concentration of solute particles and a much lower concentration of water. Unfortunately, the solute molecules can't pass through the membrane to reach equilibrium, but water molecules can. The molecules of water on the outside of the cell are going to be obstructed from passing through by the many molecules of solvent. However, the molecules on the inside have much less solvent getting in the way. Water will begin rushing out of the cell. Some water will come in, but the net movement, the overall movement, of the water molecules will be outwards, and the cell will shrink. We call this cell contraction plasmolysis. This is also how pickles are made. Now let's immerse a cell in a much less concentrated solution, a hypotonic solution. Compared to the cell, it's much less salty. Some water molecules will exit the cell, but even more will rush in because they aren't obstructed by solute particles. The cell grows in size, and it may even undergo cytolysis and burst. Placing a cell in an isotonic solution, where the concentrations inside and outside are equal, is much more pleasant. Equal amounts of water molecules continue to pass in and out of the cell. The system is in dynamic equilibrium. Particles are continuing to move, but the net movement is zero. The cell neither grows nor shrinks and is much more likely to survive. Now let's return to our seawater question. Seawater is incredibly salty, much more salty than our body's cells. Since it's such a hypertonic solution, if you immersed your cells in it, they would shrivel up and die. The real danger, however, lies in how your kidneys would react to the seawater. Your kidneys would attempt to remove the toxic levels of salt by using water pulled from your cells. Your body would actually use more water in removing the salt than was originally contained in the seawater itself. In summary, drinking seawater is a lousy idea even in extreme circumstances. You're better off drinking your own pee. So there we have it. Hypertonic,
Gross. You drink your own pee?
Gotta do what you gotta do.
Doesn't sound like good. But yes, you had to. So how are we going to measure this in the lab? We got this stuff right here. It's called dialysis tubing.
Oh, I remember this stuff.
Remember this stuff? And what you can do is you can take a strip of it. You can cut this stuff with scissors. And this is a good example of what we call a semi-permeable membrane. You can't see, it just looks like plastic, but you can't see it, but there are microscopic holes in it that can let water through at a very slow rate. Doesn't let water through very fast. But over about an hour and a half, you can see it change. And this stuff is opened on either end, and what I like to do is tie one edge of it. There's different ways to do this lab. We can tie one side of it like this, and when you guys tie these things, when we do our lab here next week, you got to tie them at the end. Okay? Make your little knot at the end. And now we've made a little baggie. Like, what are those things you eat that, like the popsicle things that you put in the freezer? Y'all know what I'm talking about?
I do.
They have colored sugar water, and they're really good. So, we're going to make one of those. What we're going to do is we're going to take a... Where's my pipette? I lost my pipette. Hold on. Get my pipette. Okay. So, we can take whatever kind of liquid we want. And you can pretend this is salt water here. And we can stick it in the baggie using a pipette. And just squirt it in there, you see. And we can get as much as we want. We can measure out different amounts if we want. We can put different liquids in here. And you can investigate how water is going to move. See, the holes in this bag are big enough to let water through, but they're not big enough to let sugar through. So there we go. I've put some water in the bag there. I can close the other end off just by tying it shut. I've made a little baggie here. Huh. Check it out. Charlie, you getting this?
Yeah.
It's a little baggie with some water. Now let's say this was just pure water. And what if I set it in a beaker full of salt water? Write down for me somewhere, or think of it in your head. It'd be better if you could write it down. Type it maybe? What do you think would happen to this bag over time if it was pure water in the bag and I set it in sugar water? If only water can cross the bag, what do you think would happen to this bag? Write it down. Write it down. I want you to think about it. And I can't guarantee you think about it unless you write it down. What happens to the bag over time, I'm going to set it in, it's pure water in the bag, I'm going to set it in some sugar water. Now, we can weigh the bag before we set it in there to see how heavy it is. We'll set it in there for about a half an hour, and then we can take it out afterward. what do you think will happen to the bag? Are you writing? What did you say? You write something? You saying the bag would lose water?
Yes.
How many said the bag would lose water? Yeah. And would you say the bag is hypertonic, hypotonic, or isotonic?
Hypo.
Hyper? Hypo? If it's just pure water, it's hypotonic. If it's got a lot of sugar in it or salt in it, it's hypertonic. They're going to get you with these words if you don't understand them completely. You could do it opposite. You could put the sugar water in the bag and you could put the pure water outside of it. What if you put Coca-Cola in the bag and you put it into a pure water? You think there'd be a difference in if you put a bag of regular Coke versus a bag of Diet Coke?
Yes.
No.
Sugar-free Diet Coke?
No difference.
I did that loud.
That's a laugh you can do, you see. Water would really rush toward the sugary Coke, and it wouldn't rush in much to the Diet Coke. Diet Coke's more like water. You can come up with a lab we can do next week. Oh, I ran out of time. You want to stop it for me?